He watched it form. In a shock chamber the size of a shoebox, under a pressure of 1.5 million bars, in less than a nanosecond, a diamond, 4.3 billion kilometers from here. That same phenomenon is happening right now, but not in a laboratory, not under controlled conditions, at a scale beyond anything we can imagine. Millions of tons of diamonds falling, right now, like hail, toward the core of Neptune, toward the core of Uranus, and perhaps even Pluto. Humanity has known this for decades. We've even managed to reproduce it on Earth. And yet, we can't go there. We can't retrieve them. And making diamonds on Earth is like burning down an entire building to heat a cup of coffee. In the next minutes, you'll understand why these diamonds are there, why we can't reach them, and why some people tried anyway. What a diamond really is. A diamond is carbon, nothing else. The same carbon that makes up your cells. The same carbon that blackens the bottom of a pot. The difference between coal and diamond is purely the way the atoms are arranged. And that arrangement only happens under two conditions: extreme pressure and extreme heat. On Earth, natural diamonds form 150 kilometers underground, under roughly 50,000 bars of pressure, and at a temperature of 1,200 degrees Celsius. They take billions of years to reach the surface. On Neptune and Uranus, it's different. The interior of Neptune, a diamond-making machine. These planets are largely composed of methane, CH, one carbon atom surrounded by 4 hydrogen atoms. As you go deeper into Neptune, pressure increases in a terrifying way. Beyond a certain threshold, around 20 gigapascals, something remarkable happens. The bonds between carbon and hydrogen break. The hydrogen escapes, and the carbon, suddenly free, seeks out its neighbors. It compresses, it orders itself, it crystallizes, and it falls. Downward, toward the core, drawn by a gravity 17 times stronger than Earth's. Crystals of pure carbon, falling through thousands of kilometers of ice and gas, like hail. Except this hail is diamond. The scale of what's falling. Current scientific models estimate that on Neptune alone, approximately 1,000 tons of diamonds form each year. 1,000 tons, every year, for 4 billion years. And no one can touch them. Problem number 1. The distance Neptune is 4.3 billion kilometers away. The Voyager 2 probe took 12 years to get there, and it only flew past. No probe has ever orbited Neptune, not one. We have a single close-up photograph. One, taken in 1989, 35 years ago. If you wanted to send an email to a probe in orbit around Neptune, it would take 4 hours to arrive. 4 hours there, 4 hours back. The slowest remote control in history. Problem number 2, the atmosphere. Even if you reached Neptune, you couldn't descend into it. Neptune has no solid surface. It's a planet of ice and gas. Below the upper atmosphere, thousands of kilometers of water, ammonia, and methane compressed under colossal pressures. Wind speeds at its surface? 2,100 kilometers per hour. The fastest winds in the solar system. 4 times the speed of a fighter jet. No material we know of could withstand those conditions. Problem number 3. The diamonds aren't waiting at the surface. And even if we descended, the diamonds aren't where we could reach them. They fall toward the core, under tens of thousands of kilometers of increasing pressure, at depths where any probe would be crushed like an empty can. At the bottom of Neptune, according to the most recent models, there may be an ocean of liquid diamond, a crystallized carbon core, a diamond boulder the size of the Earth, unreachable, forever. Let's go back to that laboratory. In 2017, at the SLAC National Accelerator Laboratory at Stanford, a team of researchers led by Dominic Krauss attempted the impossible: to reproduce the interior of Neptune. In a chamber the size of a hand, the protocol: they took a thin film of plastic, polystyrene, like food packaging, composed mainly of carbon and hydrogen, almost identical to Neptune's methane. Then they fired the world's most powerful laser at it. Not an ordinary laser. The LCLS, Linear Coherent Light Source, an X-ray beam of unimaginable intensity. For less than a nanosecond, the shock wave passes through the plastic. Pressure rises to 150 gigapascals. Temperature, several thousand degrees, in a fraction of a second. And in the X-ray diffraction data, they saw the crystalline signature of diamond appear. It had worked. Nanodiamonds, formed in nanoseconds, exactly as on Neptune. But here's the problem. To create those few nanodiamonds, invisible to the naked eye, they used one of the most energy-intensive lasers on the planet. Energy cost per shot, several $1 million. Amount of diamond produced, billionths of a gram. To produce 1 gram of diamond by this method, you would need the equivalent of an entire country's annual electricity consumption. The universe makes diamonds for free, by the ton. We burn the planet to make a speck of dust. But there's something most people don't know. Since the 2000s, several space agencies have begun seriously planning a mission to Neptune. Not for romantic reasons, for economic ones. Diamonds are not the only resource. The ice giant planets contain astronomical quantities of helium-3, deuterium water, and rare compounds, potential fuels for nuclear fusion. In 2011, NASA published its Decadal Priorities Report. An orbital mission to Uranus or Neptune was listed as a high-priority project for 2023 to 2032. In 2022, the Decadal Survey Report decided Uranus first, estimated budget $4.2 billion. Projected launch 2031 at the earliest. But orbiting Uranus is not descending into its atmosphere. It's observing from afar, photographing, measuring, understanding the structure. No one officially talks about retrieving diamonds because it's not feasible. Not with current technology, not in this century. And yet, the calculations have been done. Engineers, not dreamers, serious engineers, have calculated what it would take to send a probe capable of diving into Neptune's atmosphere. It would need a heat shield capable of withstanding temperatures of 10,000 degrees Celsius. Materials that don't yet exist. It would need propulsion powerful enough to counter winds of 2,100 kilometers per hour. No known engine can do that. And even assuming we could descend, the diamonds fall toward a core tens of thousands of kilometers deep. It's like trying to reach the bottom of the Pacific Ocean in a diving suit. But here's the real question. If we ever managed to reach those crystals, would they survive the journey back? A diamond is one of the most stable structures in the universe. Chemically, it is virtually indestructible. But to bring it back to us, you would have to carry it back up through thousands of kilometers of decreasing pressure. And there, something counterintuitive happens. Diamond is a metastable form of carbon, meaning it's stable under the conditions in which it formed. But at normal pressure, at room temperature, its natural form is not diamond. It's graphite. The pencil you use to write is diamond that failed its conversion. On Earth, your diamond rings don't turn into graphite because the energy barrier between the two states is immense. It would take millions of years at room temperature. But under the conditions of ascent from Neptune, thermal shocks, brutal pressure gradients, no one knows with certainty what would happen to the crystal structure. And the liquid diamond, there's something even stranger. At even more extreme depths inside Neptune, pressure exceeds the melting point of diamond. Diamond melts. It becomes liquid, an ocean of molten carbon in which icebergs of solid diamond may float. Researchers at the University of Chicago published in 2021 simulations showing this layer of liquid diamond ocean, several thousand kilometers thick, a sea of diamond, permanent, unreachable, real. So here's where we stand. We know that millions of tons of diamonds are falling right now toward the cores of Neptune and Uranus. We know that the bottom of those planets may hide a liquid diamond ocean the size of the Earth. We know how to reproduce the phenomenon in a laboratory. We proved it in 2017, and we can't go there. Not from lack of will, not from lack of funding, because of the fundamental laws of physics. But here's what I find fascinating. 100 years ago, we didn't know these diamonds existed. 50 years ago, we had no proof. 7 years ago, we reproduced them in a laboratory. Every time something seemed impossible, someone came along to question it. The engineers who calculated a heat shield for 10,000 degrees Celsius. The Stanford researchers with their plastic film and impossible laser. The astronomers planning a Uranus orbit for 2031. None of them will retrieve a diamond, but each of them pushes the impossible a little closer. So the real question isn't, can we go and get those diamonds? The real question is, in 200 years, in 500 years, will a civilization more advanced than ours look back and say, they knew it was there. They just didn't have the tools yet.